So we start the next session on the acquisition, automation, and movie alignment. And what we will see is the theory behind, or a little bit of the ideas behind this topic. So this is just an announcement. If you're interested in methods, there is this wiki that is, if you look for in Google for 3D EM methods, you will find the wiki where we normally put all the papers related to methodological development. And there is also a mailing list that you can subscribe, and then you will receive a mail every time a new entry is created. So finally, the first works on automation at the electron microscope were 92. So they were more or almost 30 years ago, and it is not until today that, a few years ago, that this automation has really become routinary in the lab. So there has been many advances for that, and I will mention some of them. Probably this is not a closed list. There are some other contributions, but mainly there is this autoloader that can take several grids with a robot, and then when the acquisition in one of the grids is over, then the robot takes the next one, and so on. So in this way, the acquisition can last a few days, and the keeping of the grids inside the microscope, and it is much more stable now, and even the thermal stabilization of the grid being imaged, so that there is no vibrations associated to thermal movement. Automatic focusing is also another big step forward. The acquisition software, and here I am mentioning a few. And the idea of, or the ideas related to image processing, is that you have a limited amount of time to do your analysis. And actually this slide is 5 years old, and it is already the times they are reporting, they are too long. So in principle, at that time you had 60 seconds between one micrograph and the next, and now they are not micrographs, you have movies, and you have typically much less time between one movie and the next. Currently the times are around, it depends on the acquisition scheme and everything, but it can go from 5-10 seconds to 20 seconds. And when you start acquiring, then let's say that, just for giving some numbers, you record a 4K with pixels frames with 34 frames per movie, and you do this every 60 seconds. This takes around 2 gigabytes in a hard disk. Then you have to transfer that to a computer, and that computer starts processing it. And the process is in streaming, in the sense that a new movie appears, then a new movie is transferred, and the processing of the first steps of the acquisition. And actually the current workflow goes pretty far. It can go to particle movie alignment, CTF estimation, selection of micrographs, selection of particles, 2D classification of the particles, 3D reconstruction of those particles into an initial volume, and then classifying the new coming particles into possible different structures. So, and all this has to be continuously going as new micrographs arrive. So there has been some ideas about making the acquisition more intelligent, and well, that there are some kind of fuzzy ideas of how to take decisions. And the idea is not to comment specifically on this paper, but just to let you know that there are algorithms that can help you to take decisions early during the acquisition. And then also there have been some works that try to identify those regions in the micrographs or in the grids that are more promising, because the ice is relatively uniform, or it is not. For instance, you have here the carbon hole, so the carbon hole is uniformly covered by ice, or it is not empty, or there are no contaminations, or the ice thickness is not varying too much, or whatever other reason. And these are already incorporated in some of the automatic acquisition softwares. And the point is that the more intelligence that you put into the acquisition is the more quality, the higher the quality the micrographs you are acquiring. So you can only record at a given speed. So if you can take early decisions of whether these regions are useful or not, that will impact into the number of high quality images that you have. And here is an assessment of how these decisions affect the quality of your final reconstruction, because you have fewer images, you have removed some of them, but they are of higher quality. And one of the things that was limiting the CryoEM resolution a few years ago was the beam-induced movement. The thing is that the electrons in the electron microscope interact with the sample, and the sample is moving under the electron beam. So if you average all those movements, so for instance, let's say that you take a picture with an exposure time of 1 second. So within this 1 second, you are averaging all the movement of the sample. So at the end, what we were having was something that was a blurred version of the specimen beam image. While if you fractionate this 1 second exposure into milliseconds exposure, then each one of the millisecond frames will have much less signal to noise ratio, much less contrast, but you will be able, by aligning the frames, you will be able to correctly register those frames into something that doesn't blur the information content. So here you would have the corresponding result, where you have much better structural details than if you have 1 second where everything is moving. And this is the idea behind all these beam-induced movement corrections. So the objects were moving, and even more, each object is moving in a different directions. So the movement is local, and it is not only in plane, but it is also out of plane. So we should also correct for rotations. And here you have some examples. So in some regions they may move less, in some other regions they may move more. And it is also interesting that the direction of the movement doesn't need to be the same. Sometimes it is correlated, and probably the reason is that there is some background moving solidarily, so that it is the background movement also what induces the movement of the particles. And when you correct for you estimate the movement and correct for it, you can recover the structure information to much higher resolution. So this is the power spectrum of a micrograph that doesn't move much. So here is the estimated movement, and when you correct for this movement, well, we can see more or less the same structure information as before, but the reason was that it wasn't moving much. But if it is moving much more, Then by correcting the shifts between one frame and the next, so let's say that the first frame is at the origin, and then the second frame moves a bit with respect to the first one, and then and so on and so on, then you can recover the high frequency information to much higher resolution. So here we can see how the tone rings are fading. In this direction not so much, but also we cannot see them so well. And after the movement correction, we can see the tone rings to much higher resolution. And there is also something interesting in this plot, that is, at the beginning, the first frames, it has been noted that they tend to move more than the final frames. And there might be several reasons for that. Some of them might be that the first electrons are liberating or releasing some tensions that were in the ice, and then once these tensions are released, they are no longer released, so that the sample stops moving, at least with these large movements. And here you have another related idea, that is, you don't need many particles to have high resolution. What you need are high quality particles to reach high resolution, and part of the quality is the relative movement between frames. So you have here the same structure, and this structure is analyzed under different conditions, and when you are able to align correctly the frames and correct for this beam-induced movement, then you are able to recover with many less particles. You are able to recover a much better resolution structure. There is also a debate of which are the frames that we should use for 3D reconstruction. So, for instance, if I may choose all of the frames, or I may use only the ones from 3 to 15, or just the first ones. So that is really a lot of possibilities, and maybe this debate was a few years ago, but now things are solved in a different way, I would say. So first, this dose weighting that we do at the beginning, I don't think it is the best thing, because those parameters so the dose weighting somehow dampens the contribution of the frames with more radiation damage, but those dampening coefficients, they were measured very accurately for a particular acquisition, and they cannot be applied universally everywhere for all experiments. Now I would say these weights of the different contribution of the frames are measured at the level of polishing. So once you know your structure, you compare your structure to the frames, and then you decide what is the radiation damage and what is the quality of each one of the frames, and then the higher the quality, the higher the weight will be. So there is no longer this need for choosing which frames should be used for the 3D reconstruction. And this paper, I like it a lot. This is a paper in which Robert Glaser explains possible reasons for the beam-induced movement, and there are many of them, and some of them are shown here, like an elastic scattering that deposits energy, and then this energy makes the sample move, or that the protein is damaged, the vitreous ice is damaged, the ice may get thinner, a number of chemical reactions that are happening there and that might be liberating gases, or whatever the reasons are. Probably there is a mixture of reasons in every acquisition, and the dominating term may be one of them, in each acquisition a different one, or even a mixture of all these possible reasons. And the radiation damage is also amino acid dependent. So different amino acids at different doses get damaged in different ways. So it is not only that it is acquisition dependent, but also sample dependent and chemically dependent. So it depends on the chemical structure that you are looking at. And here are some other reasons that there are ice bubbles of hydrogen that are formed, the release and creation of mechanical stresses, the charging that may deflect the incoming electrons. There is a doming probably of the sample and the ice of the sample under the electron beam, and this doming may be caused by this inhomogeneity, possible inhomogeneities of the electron beam. And here you have a number of papers that you may consult for this. So once we understand that the sample is moving, we may try to correct for this movement. And one possibility is to use a global shift correction. So let's say that we have two frames like these two, and we want to compute the relative shift between those two. So we can use any way of image correlation. Here it is shown phase correlation, but we compute the correlation between these two images, and then the peak, the location of the peak of this correlation will tell us what is the relative shift. Here it is something like 50-50 pixels. And we can do that for every pair of frames, so that for frame I to frame j, we can compute what is the relative shift between I and I+1 and I+1 and I+2, and go so on until frame j. And then the addition of all these relative shifts should be the shift that we have observed with between frames I and j. And with all this information, we can solve for an equation system in which the unknowns are the shifts between frames, and this is an overdetermined equation system, and there could be different ways to solve for that equation system. For instance, MotionCorr, the first MotionCorr and MotionCorr 2 was solving that in a least squares way. XMIP was trying to detect outliers and a robust estimation of these, removing errors in the estimation of these frames. The reason is that the frames are so noisy that the correlation peaks are not so clean as in this example. You might have many mistakes, and then solving for the shifts in robust way is really important. MotionCorr 2 gives more freedom, so it tries to explain the doming in space, and it also adds some time dependence of the doming or the shifts, and at the end this causes or this allows for identifying local movements. And here is a summary of what is the global trajectory, but this global trajectory can also be decomposed into local movements of the different regions. And why you may have different movements is because this doming causes the different regions to behave differently if you are in one of the corners or in the middle, and this is especially true if you have a tilted sample. And what they show is that if you correct not only for the global shift but also for the local movements, you get better resolution. And how to estimate the local movement may vary between different packages. So for instance, this was one of the first tries or attempts to correct locally also. So this was done at the level of particles, and they were trying to detect a linear a linear trajectory for that particle. And for instance, optical flow is another one that is really free. It allows every point to have its own trajectory, so a little bit it is represented here. So you have 2 frames, and then every point has a different path. And this is very rich, but it also took a lot of time to compute. And then now we have in XMIP you have still the optical flow available, but we are also promoting the use of some other algorithm that is used based on B-splines. So the main point is that the movement is local. There are different ways of estimating what is the local movement, either for patches of the micrographs, either for the particles, each one of the particles. This is also part of the alignment that you do at the polishing at the end. But all of these that we have discussed so far, they are talking only about movements in plane. But probably what is also happening is that the movement is out of plane. So this protein inside the ice embedding is moving, is rotating out of the plane that you are imaging. So these rotations, for the moment, I'm not aware that anyone is correcting for them. And there is this idea of dose compensation or dose dampening, or giving less weight to those images that have been more damaged by the radiation. And here there is a very accurate study in which they collected 70 or 69 frames, and if you make a reconstruction with the first frames, the reconstruction was had much better resolution than the reconstruction performed with the same number of frames, but at the end of the acquisition. So these latter frames, they were more damaged by the electron beam because they were exposed for longer. And then they computed some curves, or what was the damage caused as a function of those. And this damage and these coefficients, they have been incorporated into the motion correction algorithms so that you can give less weight to the final frames. But as I said before, these coefficients were very accurately measured, but they are not universal for all microscopes, all samples, all acquisitions in the world and history. So sometimes they work and they help to get better resolution, and sometimes they don't work, and they don't work meaning that they don't help, or they even make more some harm. And I would say that now maybe the trend is to correct for, or to look for these weights in a way at the end of the processing through the polishing. And here is another example of how this dose compensation can help. And there is a relationship also between number of particles and resolution. So the more particles you add, the better the resolution will be. So that is explained in this slope, and the change between these two curves is because of the dose compensation. And yeah, also something interesting to point is that the relationship between resolution and number of particles is not linear. So there is no, you may look at this axis. This axis is in logarithmic scale, so meaning that the resolution that you can achieve depends logarithmically with the number of particles. And another very interesting thing that we should think of when we are acquiring images is that there might be small differences in the magnification in each one of the directions. So the magnification in the electron microscope is determined by electromagnetic lenses and the currents in those lenses, and these currents may not be exactly the same in orthogonal directions. So that is translated into slightly different pixel sizes in each one of the directions. And there was a study trying to measure those anisotropies, and they reported a 1 to 3% of differences in the pixel size. And that difference, if you look at the projection of a single molecule, you barely see the difference, but if you subtract those, you see that there are significant differences, especially as you go away from the center of the particle, where all these scaling factors are magnified. And the difference between compensating for those possible anisotropies and not compensating for them can be as striking as the difference between these two structures. So one of them is without correcting for it, and the other one is correcting for it. And this is something that currently I would say most of the programs do, XMIP for sure, and system I think it does too. And then about the rest I'm not so sure, so I cannot say whether they do it or not, but I don't say they don't do it. Another effect of this anisotropic pixel size is that the CTF correction also changes with the direction. So the CTF depends on the defocus, and we know that the defocus may be astigmatic, but it also depends on the pixel size. And these small differences in pixel size make that at the beginning the CTF more or less they're not terribly different, but at some point they can be totally out of phase, like in this at this very high frequency. And this happens because of the differences in pixel size, because of differences in defocus, and any other factor that may make the acquisition anisotropic. And here is a theoretical paper where they analyze the limitations that or what could be the factors that could limit the resolution or high resolution structures in CryoEM. And one of them that they reported was the accuracy in the determination of the defocus. So if you want to reach, for instance, a resolution of 3 angstroms and you're using a microscope of 200 kilovolts or 300 kilovolts, you need to estimate the defocus with an accuracy that is better than 179 angstroms or 200 angstroms. So that means you need to be very accurate in the determination of the defocus, because otherwise at 3 angstrom resolution, that is a high frequency, you are already with these out of phase CTFs in different so you think that the CTF is one, the true CTF is another one, and at 3 angstroms they are already totally out of phase. Here is a table from the CTF challenge summary. So there was a challenge about estimating the CTF defocus, and most of what we learned in that challenge is that the differences between different algorithms were in the order of 200, 300 angstroms. So for the same micrograph, you estimate with different methods, and the different estimates differ from each other in the order of 200, 300. So we are already in this regime where our errors, estimation errors, are in the order of those errors that limit to 2-3 angstrom resolution. So if you want to achieve very high resolution, you should better use very accurate methods. And here at that time The best ones were CTF Fine, XMIP, or Appian. And not only that, it is that you should average the results from those programs, because it doesn't matter how accurate they are, they will commit errors, and these errors will tend to be hopefully randomly distributed. So if you average several estimations, you are reducing the estimation error. And there is another effect that prevents high resolution. That there is a defocus gradient. So this defocus gradient makes that the upper part of a specimen, has a different defocus from the lower part of the specimen. And if you want to reach very high resolution for big objects, these differences have to be explicitly taken into account. And this is the idea that is behind this equal sphere correction. So the point is that the projection that you have in the microscope is not a plane of the 3D Fourier transform, but it is on the surface of some sphere, and then you have to place back correctly the 2D Fourier transform into the 3D Fourier space, not line on a plane, but line in this sphere. And then this was also analyzed by this theoretical paper, and this is the resolutions that if you want to reach, for instance, 2 angstroms resolution, you are in a 300 kilovolts microscope. Then the maximum diameter that is not limited by this defocus gradient is something around 250 or 300 angstroms. So if you want high resolution for large objects, you need to correct and to account for these small differences in the focus. And and actually the thing is more complicated, because it is we have a paper. It was about something different. It was X-ray microscopy, not electron microscopy, but the analysis was similar. And the thing is that as long as you consider the focus gradient, then the information is not coming from exactly a surface, but from a region. So it is a whole region that is contributing to the 3D Fourier transform. This is another interesting idea. These particles are not all of them at the same position in the ice layer. So this is a paper in which they analyze many grids, and in these grids they found all possible kinds of configurations. So configurations in which the ice was pretty homogeneous, but it was tilted. So particles here, they had different defocus from particles there, or you had this disposition in which some particles have a defocus, these other particles have another defocus. Within a layer, you might have a whole distribution of particles within the ice layer, and you could have many different configurations, and every particle had a different height within the ice layer, and different height means different defocus. And there are some ways of correcting for the defocus gradient, especially for tilted micrographs. And here you have this paper of geometrically optimized CTF determination, where they explicitly take care of the tilt of the sample, so that different regions in the micrograph have different defocus. And here is another interesting idea. So in one of our papers, we reported that despite the fact that when you average, you see nicely the the tone rings, so going up and down in the spectrum, it is not that you have to average through. So if your images are astigmatic, you have to average along equivalent phase points. So all these black points or all these white points, following the shape of the ellipsoid. But it is also that the noise underneath is also astigmatic. So the noise, it is not only that the defocus is astigmatic, but the noise is also astigmatic. And then you need some way of estimating this astigmatic noise shape. So all these tools that only work with 1D radial averages, they might be missing the astigmatism of the noise. Something more to take into account is that there are microscopes that are corrected for the spherical aberration, and if you go to material science, all the high resolution structures, they are estimated, or they are imaged with these aberration corrected electron microscopes. And in biology we don't find this need much often, but you have some papers by Holger Stark, for instance, in which with a CS corrected microscope they achieve very high resolution. So this may be also the future. And for these CS corrected microscopes, and well, there are some ways of estimating what is the effect of the CS in different regions of the micrograph, and correcting for those. And all this goes into the direction that very accurate CTF correction is certainly the way to go to achieve extremely high resolution. Face plates, there was a period 2-3 years ago in which they were very popular. Especially they are very good for imaging low weight macromolecules, because they increase a lot the contrast. So this is the contrast that you have with a standard microscope, and this is if you put a faceplate along the path, and then the faceplate shifts the CTF from starting at 0 or almost 0. You may have noticed that all these CTFs, let us look at this one. So this CTF starts at 0. So 0 is a constant. So it is the DC component of the image, the low frequency component of the image, if you want. So they are blackout. So they are removed from the final micrographs, and that is why we have so little contrast. But if you now make the CTF to start, instead of starting at 0, started at 1 or a number close to 1, then you see the particles very well with very high contrast. There are also a number of issues regarding faceplates, and now I don't know if the wisdom is that for very high resolution faceplates are not helping, but for medium, even 3 angstrom resolution, for low weight macromolecules, they can be very helpful. And here you have some examples of structures reconstructed with faceplates. And yeah, that is a problem with the faceplates of estimating the defocus, because if you shift by 90 degrees, you barely see the tone rings, and then you cannot estimate correctly what was the defocus. So I think that the trend now is to use faceplates, but with a little bit of defocus, so that you can see tone rings and you can fit them. And there are some other issues that may be preventing us from reaching very high resolution. One of them is this dynamic electron scattering. That is, an electron may interact with one of the atoms of the sample and then deviate and then interact again, and this multiple scattering is not contemplated by the theory of the CDF. So the CDF assumes a single scattering event, so that happens for thin objects, and if your object is not so thin, the probability of multiple scattering increases, and then this again might be limiting the resolution of your final structure. Then more things related to the acquisition is the gain of the camera. So when you are acquiring your images, you are recording the electrons arriving to the direct electron detector, and this sensor has so it is an electronic device, and this electronic device somehow depends on local currents of different transistors, circuits, whatever, and this causes that the same amount of electrons reaching to two different points, because of the different properties of the sensor locally, they may report different number of counts, and they have different efficiencies. So that is called the gain image, and this gain image can be estimated, can be measured experimentally, but it can also be estimated from the movie itself. And here you have, for instance, an estimation of the gain corresponding to this movie. So we can see that it is a pretty good estimation. And here we have the residual gain, for instance. So the residual is when I have estimated this, or when I correct with the experimental image. So what is the remaining? And the remaining might be should be 1, or small fluctuations around 1, and it might be this thing, or in the case that you have not corrected correctly for the gain, then you see your particles in the residual image. So if you see your particles, that means that the gain has not been correctly compensated. And that is also the beam tilt. The beam tilt also is translated into a phase shift of the CDF. The idea is that the beam is not completely parallel to the optical axis, but it has some angle. It can be even divergent. So at the origin it has some angle, but then as you go away from the origin, it has a different angle. And if you don't estimate these angles, you are limiting your 3D reconstruction, the resolution of your 3D reconstruction. And currently, beam tilt is not accidental, but it can be induced on purpose. And the reason is that it allows a much faster acquisition. You have to compensate to measure it later, but it allows a much faster acquisition. So all these very quick acquisitions with 5 seconds between movies is also because of this use of beam tilt. And yeah, the beam tilt, this is just a slide that it emphasizes that the beam tilt is one of the optical aberrations that can be estimated in the same way as you estimate defocus, astigmatism, coma, spherical aberration, or whatever. And yeah, this idea that you can use the beam tilt and the beam shift as a fast acquisition tool, and then this doesn't affect much the resolution as long as you stay at relatively low resolution, or you don't low resolution, meaning that 4:3 angstrom resolution. And if you want to go further, you need to estimate the beam tilt and correct for it. There is another idea related to micrographs, that is the use of smaller micrographs. So these micrographs sometimes they can be really, really large, like 8K, with a very, very fine sampling rate of pixel size. And you know, for instance, let's say that your pixel size is 0.5 angstrom per pixel. So you know that Nyquist there is 1 angstrom, and you know that your structure will not reach 1 angstrom resolution. So you want to use a smaller micrographs for several reasons. They occupy less space, they make your algorithms run faster, and there is a much more fundamental reason, that is, if you make them smaller, you're removing noise, and then this noise removal will help the algorithms to align the images. And there are different ways of doing the downsizing. So one of them is called binning. So binning is just if you want to make it twice smaller, so you take squares of size 2 by 2 and then you average those numbers. That is the pure binning. But that is the worst way that you can do it. At the moment, I would say no package is doing that. At some point in time, they were all doing it that way. I would say that now they are using normally Fourier cropping, and this Fourier cropping is actually the right thing. And if you want to do it in real space, you could first convolve with some kind of filter like this one, and then do the downsampling. So the right operation is put an anti-aliasing filter and then do the downsampling, or do the Fourier cropping. That is the way it is done. But if you do binning, this binning is affects a lot in the Fourier shell correlation, for instance. What is the power spectrum of the resulting images? So they can be really, really harmful. Another interesting idea related to this acquisition is the possibility to compress the original information into file formats that occupy less space. And image compression can be lossless, so you haven't lost any information at all, but they compress less. Or it can be lossy, so you can lose a little bit of information, but then you can compress much more. And this paper, they analyze what is the effect of on the Fourier ring correlation of images that have been compressed by different factors. And what they show is that a little amount of compression, even if it is a little bit lossy, doesn't have a very severe effect on the 3D reconstruction. And here is some illustration of this is the raw data, and this is the same data with the JPEG compression, and this is the resolution in as measured by the FSC, and with a little bit of compression, a little bit more of PNG, for instance. So in conclusion, let us say that there are many ideas related to the intelligent acquisition and efficient use of the electron microscope, and there are a lot of filters to estimate, or a lot of algorithms to estimate the quality of the different micrographs. And the BIM-induced movement was actually one of the main steps forwards to have a high resolution. And dose compensation is also an issue, and normally now performed at the end of the processing. And then you have to do very accurate operations to estimate correctly the magnification, all the CDF parameters, and all the possibilities that high frequency components have been treated in slightly different ways. It depends on the particle, depends on the location of the particle, and so on. And if you do downsampling, do an accurate downsampling. I would say that most of the packages now, they are doing very accurate downsampling. That was not the case a few years ago. And I would worry first about accuracy and rather than speed. So we all like this real-time processing at the side of the microscope, and this is fine, but we should be aware that that very quick processing may not be the best for the final reconstruction, or if you want to make very accurate estimates at the beginning, corrections at the beginning, then you may be ready to pay some time for that. And that would be all, and see you in the next session.